Hi, my name is Mike Bundock. I'm founder of AugView. Just imagine you're out on site. You're about to install some new fiber optic cable. What's the one superpower you'd really like to have? For me, I'd like a superpower that showed me exactly where all the existing assets were located. You know, what they are. Are they live or are they abandoned? How big are they? What's their specification? How deep are they? That's the superpower I would like. Well, maybe I can put my glasses on. Nah, just kidding. A few years back, we were porting to augmented reality glasses. And they looked like this. And they had a whole computer attached to the back. So that didn't really work. More recently, they look like this. And these actually work fairly well indoors. They have some good capabilities, but not so good outdoors. Very recently, they started looking like this. Now these have GPS included, full tracking, surface tracking, SLAM algorithms, 5G, and I can see into the ground to see where my pipes and cables are. Now we're talking. So what we're going to cover is the definitions of what augmented reality is all about. We're going to look at why is it beneficial? Why bother? What is it? Why do I think it's important? We're going to look at the use cases for AR. So visualization of both physical assets and their characteristics. That's what primarily, and also some data capture improvements as well. And we're going to look at what are the technical challenges, for both just getting data to the device and also then all the technology that's actually in these amazing headsets that are being produced now. So associated with the optics, the tracking, the sensors, and how we interact with the device. So what is augmented reality? Well, basically, it's overlaying something that's virtual onto what we can see of reality. It's a pretty generic term, and I prefer to use the generic term rather than some of the more specific niche terms such as mixed reality. Mixed reality became a bit of a marketing term for one or two of the vendors that started playing in this space. But I think in actual fact, AR is a better term to use because it covers a raft of different use cases, both, and we'll see that. So I'm going to use the terms augmented reality and AR throughout. It is a bit of a continuum because when we look at just our reality around us, if we start adding little bits of virtual things on top, then that's augmented reality. If we come from the other end, where everything is virtual, and then we start making parts of reality visible, well, sometimes that's termed augmented virtuality. And we can do all sorts of different types of augmented reality, things that are actually geospatially positioned, locked in space, and we can interact with them. And that was the mixed reality term. But also sometimes actually augmented reality is just augmenting something in some way. It doesn't have to be out in the real world. It can actually be sitting on your desk and you're augmenting it in some way. So it's a generic term, and I think I prefer to use that generic term in its widest sense. So what's it all about? It's all about comprehension. It helps us understand, comprehend what is somewhere, what is where. So what are the pipes or cables or conduits or things that are below my feet in the ground? Whereabouts are they? How deep are they? How big is it? That sort of stuff. And it's because the device knows our location. Our devices, our tablets, our phones, our AR glasses now are understanding where we are placed physically in the real world, and also how we are oriented. How is that tablet or phone or glasses, how are they oriented in the real world? So they have sensors in them to tell us, where we are located and where we're looking. One of the advantages of AR is there's no mental model mapping required. When we look around, we can see a virtual object in a particular location. It looks like the real objects, right? We don't have to do a mental model translation, which we do when we're looking at plans, bits of paper with lines and points and polygons on them, or PDF equivalents. Okay, so there's no mental model translation. Memory retention is another big deal with AR. Apparently, it stimulates our brain in some way that just looking at a piece of paper or a plan doesn't do. It's, I think, a bit the equivalent of looking at something on something that is real, or looking at something on TV or a moving image. It engages quite a lot of our brain in understanding, but there's no translation required. So what it does, it actually helps us both comprehend and retain what it is, our understanding is. So we can use it for features that we cannot see. So we can display things we can't otherwise see. And we can also display characteristics of features that are not visible, like temperature, voltage, current, is it live or dead, so on. So all sorts of ways of actually being able to use augmented reality to display things. So we can display what something is, where it's located, its extent, maybe is it existing or proposed or historical, and then we can also display its characteristics, and we can use different ways of displaying those characteristics, or even the definition of the object. We can put labels on items. We can actually give them fuzzy extents for QL codes and spatial accuracy. We can actually display the actual survey observations that were used to capture where this thing might be. And we can actually display those little observations with little spheroids that represent the survey accuracy of that original survey. Or we could display it based on QL code tolerances and so on. For linear features, pipes, cables, conduits, we might want to display two parallel lines within which we know that asset is. Or perhaps we want to display it in terms of a cuboid, or perhaps a fuzzy elliptical cross-section sort of shape. Depends on how sophisticated we want to get. So lots of different ways of being able to display assets that give, in this case, information about spatial accuracy that was used at the time that it was captured. Obviously, we can use things like physical characteristics to display. If we have an attribute of diameter, then we can display the pipe or cable or conduit in the appropriate diameter. If we have an attribute of material, it may be metallic or plastic or painted or something, then we can actually display it in an appropriate type of material. We can display things structure. We could actually display all the complexities of a valve or a hydrant or some other pump or piece of plant. And we can also actually have links to their specifications. So one of the nice things about AR is, especially AR stimulated by recognizing a feature, so image recognition, then we can actually immediately, if we recognize the image, then we can actually associate the specification and get the model that exactly matches that specification in its right location and its right orientation. We can use dynamic attributes and visualize those. So we might be getting IoT feeds from sensors that display maybe the wind speed, the voltage, the temperature, the current, the pressure, the depth of water in a manhole, the toxicity of the gases. And we can display those either as instantaneous values on a banner or historical values as a graph, or perhaps we want to actually display it in color or in dynamic models, so we can see the water going up and down in the manhole and the color of the gas changing as it becomes more or less toxic. We can use SCADA inputs to actually display state or status of things as well. What is the loading on the transformer? What is the amount of current going through the line? Is it powered up, or is it safe to actually interact with? So on. So we can use those to actually to using color or symbology or graphs or dynamic models and so on in AR. So we're adding a lot of information, making the user be able to comprehend what's happening to that otherwise static piece of cable or otherwise static manhole. We can actually see what's actually happening inside it or to it. So this is an example where we're integrating IoT data, in this case displayed in virtual reality. This manhole has a sensor in it, and it's monitored, and the instantaneous values of gas concentrations and water levels and flow rates and so on are displayed as instantaneous values, or they can be displayed as a graph, and you can interact with them by selecting the appropriate attribute and interact with it backwards and forwards. And also the model's dynamic, so the water level goes up and down as the water level changes, and the color of the gas changes, as I mentioned before, as it becomes more or less toxic. So there's a lot of information being conveyed without having to pull the lid of the manhole off. We can actually display the accuracy of the survey. We can get immediate feedback on both how accurate was that recorded position, because our GNSS units actually feed back to us what the accuracy they're getting from the corrections and the baseline length and so on. So they can actually give us information about how accurate that GPS position or GNSS position is. So we can display that as a small spheroid of the appropriate diameter, showing us what that expected accuracy is. We can, if we sample over time, the GP, if we're static and we sample over time, then we can record things such as the standard deviation of error from the mean position. We can determine the 95% confidence interval, and so on. And so we can use those and to actually display circles of the appropriate size, giving us feedback immediately on the accuracy of our observation. We can also, when we actually capture the physical asset, so we might go around the outside of perhaps a pit or an underground utility box, and then as soon as we actually say, yep, we want to capture that, it's a specific specification, then we can immediately see the 3D rendition of that in augmented reality. And we can check, is it oriented correctly? Is it the correct specification? Does it match what we see in reality? So we get immediate feedback in real time. So I think that really improves data quality and also in-field data capture, and there's no post-processing required in the back office. So what are the technical challenges? Data is obviously a challenge to anything that's out mobile. We want to be able to see all of the assets in the ground, not just perhaps if I'm working for a water authority. It's all very, very, excellent for me to be able to capture my water authority data and the manholes and the catch pits and so on. But if I want to go dig a hole or repair something, I want to know what else is around there. So we really want to access all the data from all the different sources. And so we need fast access to all data sources. We're going to have a look. We're going to look at the technology inside the AR glasses, the optics, the sensors that are in there, the surface tracking technology that's in these as well, and also how we interact, because we've lost our lump of glass that we've been carrying around for the last 30 years. So we don't have that to tap on anymore on menus. How are we going to interact with it? So let's get into that. Data must be complete. Data must be current, and it must be of known accuracy. So the best source of data is always the asset owner. They have a vested interest in getting their data up to date, highly accurate, and complete. And wanting to be able to publish that so that other people don't go and damage it or dig it up. Okay, so asset owners have a real vested interest in getting their data complete and correct. Users need to get access to all of that data, as I mentioned before, not just one particular utility. So best source is from the asset owner. And it's very easy these days with GIS web servers to actually get highly secure, highly accurate data directly, typically from a synchronized replica, but within the DMZ of the asset owner's servers. Asset owners use different types of GIS systems. Some will be using Esri, some will be using open source, some will be using Small World, some will be using Intergraph, some will be using other systems. All right. So there are many different types of GIS system out there, all with their own data models, and some of them have got their own APIs. Some of them use open source, open standards from OGC. But so we need an environment that allows us to communicate simultaneously to all the different data sources with the appropriate APIs to talk to them. I have yet to see a centralized system ever work for more than a very short period of time. It very quickly becomes out of date as people buy new different GIS products, and the schemas will change and so on. So it's very hard for a centralized system to really work for any length of time in an integrated way. So federated databases approach is really our preferred approach, and it gives us that hopefully complete, current, and of known accuracy data. Within our AR glasses, we really want high resolution displays, and they're starting to be available. So the 1024 by 760, a minimum sort of resolution on each eye. They need to be usable in bright sunlight and also in the middle of the night. So we need to be able to see technologies evolve that incorporate the LCD change light sort of systems that you might see on privacy screens, where a voltage is applied to an LCD screen and it'll go gray and protect. And so that's a dimmable, controllable filter that allows the right amount of light coming through. from the outside. So controlling the bright sunlight and daylight, midday, and then being totally transparent at night. We want a wide field of view. Our eyes actually see a very wide field of view, around about 180 degrees roughly side to side, and about 120 vertically. Yep. At the moment, the AR glasses that we're talking about at the moment have around about a 45 to 50 degree field of view on the diagonal, which is a lot less. Historically, the first glasses I showed you at the start of the presentation from Meta, they had a 90 degree field of view. Fairly low resolution, but it was a 90 degree field of view. So we've stepped back in many ways, but the technology is improving all the time, and we expect to see 90 degree field of view glasses become normal. Eye tracking is one of the technologies that's used to keep track of where you're looking. It tracks your iris. And that is used often for controlling the resolution dynamically on the screen. So giving us high resolution at the location we're looking, lower resolution in the periphery. A good technique for actually reducing the amount of effort that actually goes into producing a high resolution image everywhere. We do need binocular. Our eyes are very good at determining distance and depth. So distance from us, distance perception is very important. So we really do want that binocular vision for depth perception. And we want it to be believable. We really want it to be for features to look like either what they really do look like, or a rendition of them that conveys additional information by colorizing them or something to convey some additional information. For instance, like, is it live or dead? Is it water rather than stormwater? Optics is a critical part of AR glasses. Also in AR glasses is technology to keep track of where we're looking and where we're located and how we're moving. This is the IMU. It usually houses three sensors: a 3-axis accelerometer, and that measures tilt. So it's really measuring the force of gravity or linear acceleration. So it understands the tilt of the phone or the glasses. The gyro actually measures rotational acceleration primarily, and also some linear acceleration. So it is used in conjunction with the accelerometer to take out sort of constant motion. And also the magnetometer, that actually is again a 3-axis sensor, and that measures the Earth's magnetic field. And so it determines where magnetic north is, magnetic south is, and how we are oriented in relation to that. Now, the magnetic field is easily interfered with, so the magnetometer actually is the worst of the three sensors. It's very easily affected by charging your device, leaving it near something charging, moving lumps of metal like trucks and buses and cars, and also transformers and other high voltage things outdoors. So many things can impact that magnetic field. Sensor fusion can be used to actually help reduce some of these sensitivities, like in the magnetometer. And sensor fusion can be used to take all three of those inputs and actually then determine what our real linear acceleration is horizontally, where we're looking, how we're tilting our head or tilting our phone or tablet. And it can also be used to give us an estimated location if our starting position is known. Now, large systems on ships, on aircraft, and so on, also integrate these same sensors, but more sophisticated ones than are in our phones and tablets. And they also integrate RTK GPS, so they get high accuracy integration of GPS position as well. And some of these devices, can measure all sorts of movements on things like boats, the yaw, the pitch, the heave, as well as other sort of linear acceleration and so on position. And they can give high accuracy position. We have very much smaller sensors in our phones and tablets, and often you call them termed MEMS chips. And these are amazingly very small electromechanical devices, actually. If you've seen electron microscope pictures of them, they have little gears and wheels and it's bizarre. Anyway, but they're not accurate, not over long periods of time. They're very susceptible to bias, and so they will actually, if we just rely on the MEMS chips themselves, we'll see that our position quickly accelerates away without other inputs. And the input we take in is obviously RTK GPS or GNSS, and that then gives us updates all the time on our actual recorded position. And then we can integrate sensor fusion with GNSS inputs to give us smooth movement between updates of our GPS position. So that's how we actually track our location. So I've just mentioned this GPS or GNSS systems. I'm sure you all are very familiar with these. I'm not going to go into this, but typically what we need in terms of surveying for utility networks is that sort of 5 to 10 centimeter accuracy. We can't dig a hole less than about 30 centimeters across. Most of our assets are at least in the sort of the 5 to 10 centimeter cross-sectional diameter sort of range, and we also have other inputs to other issues that we need to think about, such as tectonic plate motion. But I'm not going to talk about that today. It's a whole presentation in its own right. So typically, I'm sort of suggesting we really need sort of that 5 to 10 centimeter accuracy from our RTK GPS systems, GNSS systems, and that will actually give us then the desired accuracy for refinding assets appropriately under the ground. So what is SLAM? SLAM is some software that actually is like real-time reverse photogrammetry. I'm old. I was working in the Department of Lands and Survey when I first started working many years ago, at 1979. So photogrammetry was a big deal then, and so now we're essentially doing the reverse of photogrammetry in real time to determine our location from the video stream that's coming in, or perhaps from other techniques such as LiDAR, but mostly from the video stream. It's a standard part of iOS and Android now. So ARKit on iOS and ARCore on Android. And these are surface tracking SLAM algorithms that track our position by detecting surfaces and significant points in a video scene, and then tracking our location in comparison to those points in the scene and the surfaces. There are other versions of it and other SLAM SDKs that are available. And all of the AR glasses that you'll be looking at all have their own flavors of surface tracking technology, or SLAM technology, that we can use to actually control our relative position and our relative orientation based on our starting position. Okay, so SLAM and surface tracking give us relative position and relative orientation. So we have to know where we're starting from and where we are initially looking. It can be surprisingly accurate over quite long distances, even out to like 50 meters without other inputs. So as long as we know exactly where we're looking and where we're based to start with, I can track 50 meters and know exactly where I'm going to be at the end to within 15 to 20 centimeters. So that's remarkable, just using an ordinary phone with no GPS or GNSS inputs at all. Okay, so I can use that, integrate it with GPS updates, GNSS updates, and then I really have good control and good confidence in my position. How do we interact with our AR glasses? We've thrown away that big lump of glass we've been carrying around for the last 30 years. So we don't have a menu, a lump of glass to tap on. Instead, what we can do is we can actually project menus or user interface components either onto a wall, or have them surrounding and fixed relative to our point of view, or we can actually paste them somewhere in space. We could also paste them onto the back of our hand. So this might become my menu. We can also use speech recognition. So we can say select item 1, select asset. We can use finger tracking. We can actually use finger tracking to select items. So we could actually maybe use a pinch or a point or some other technique for actually grabbing something and moving it around. Some of the things we might want to move around are menus. We might want to grab a menu, move it around, paste it somewhere. Or we might want to select an asset, display its attributes, and then scroll up and down the menu to be able to update, maybe select one of the items from the menu, and then use voice to capture the attribute value. One of the things I found really disconcerting when I started using augmented reality with glasses was that there was no haptic feedback. I was used to tapping on that lump of glass. And now with my finger, it just disappears through the menu. So how do I get feedback that I've actually selected it? Well, we can do is we can actually make the button move, we can make it flash, and we can make a little sound that we can hear. So as we touch it. So lots of techniques for feedback, but we don't get that touch sense at the moment. Haptic feedback gloves are actually under development, and there are prototypes and there are some I think available now, but they're probably not good enough or usable enough for our target audience, which is the fat-fingered engineer working at 2 a.m. in the morning to fix a broken water main. So we want to have something that's actually bulletproof, ruggedized, able to be used in adverse conditions, rather than something that can just be used for demonstrations in the office. So one of those devices that we've just come across is the Roku DevCraft. So one of the devices we've just come across with many of these characteristics is the Roku DevCraft. In this case, I've mounted it. It's designed to be mounted onto a helmet. And so it's a set of glasses, has a processor at the back and a GPS unit at the back, and a good-sized battery in it. So it's ruggedized, designed for the petrochem industry in this particular case. 8-hour battery, GPS or GNSS built in, so both Baidu and GPS satellite constellations are in this particular early version. Supports SLAM algorithms for surface tracking. Has a 45-degree field of view. Runs on Android. Integrated 4G, 5G communications, plus Bluetooth. It does finger tracking, so I can track my fingers and I can select things. We tend to use the pinch item for selecting things and moving them around. It understands my voice. I can talk to it. I can say, select an attribute, select an asset, and so on. And it also has controls mounted on the sides, either as rotational dials or little buttons. So I can use buttons and dials to actually to control the device. So a pretty useful device. And that's the first one that we found that is actually ruggedized and designed to be used out for our target market. Sia, thanks for actually listening to the presentation. And if we have time for any questions, I'd be very happy to take questions. But I think I'll pretty much use my 30 minutes. So thanks very much.
Hey.
Hi.
Thanks so much. What a fascinating presentation. I don't obviously have that equipment, but I just got an Oculus Quest 2 a couple of weeks ago, and I've been just amazed at that experience when you're talking about responses and the haptics and things like that. Let's get to the questions. I'll dive right in. We'll go into our break a little bit. There's one here. In AR, how do you deal with the often low quality underground data from network owners?
There's lots of different ways of being able to display the data. I mean, obviously, we've already sort of started mentioning things like color and shape and so on. But some people are familiar with if you get a mark out on the pavement, then typically they'll give you some sort of estimate of the accuracy of the location by perhaps putting a marker down the center in standard color for the asset type that's being identified, and perhaps 2 little parallel lines running parallel with it. That technique is great, certainly works in some situations. Alternatives are that you can actually have 2 representations for the same feature, basically, the actual, maybe the pipe or conduit or cable being displayed in what we think is its database location, but also then actually surround that with a transparent other volume. And that could be something like a cuboid, which, if you know what the approximate horizontal and vertical accuracies might be or tolerances might be, either based on the QL code or based on other survey information that you might have. And so you can use, sort of a cuboid type shape to display it. We've also tested with using elliptical cross-section sort of shapes, because if you have an expected vertical accuracy and an estimated horizontal accuracy, then really you're probably looking at some sort of oval sort of shape that you're highly likely to find that feature within. That became very confusing because it's hard to see what the edges of that represent. So I think the parallel lines on the surface were certainly sort of useful. Another one is actually just using a plane, a horizontal plane through the feature. also that actually was more understandable, comprehensible, in the same way that the parallel lines are on the surface. So yeah, those are the different techniques. Some of our different customers have used different techniques for doing that.
I wanted to talk to you a little bit about customers and markets. We're the underground mapping forum. Utilities are obviously the big focus.
Yeah.
Who's most excited about your technology when they learn about it? There must be so many different verticals that are interested in using this.
Yeah, our earliest customers, we started back in 2012, and we were definitely pushing the limits on the technology in 2012. And our first customers outside of New Zealand was a Malaysian water authority. And so now we have multiple customers up in Malaysia. And the first water authority is still a customer. Power companies, our largest power company customer is Tata Power in India, Tata Power Distribution in Delhi. You can imagine the problems they have both underground and overhead networks in an environment like Delhi. Just recently, also getting involved in a lot of sort of environments where they have combined utility responsibility, like universities, port authorities, airports. They essentially become a combined utility because they become responsible for all of those pipe networks, cables, and so on that are within their the bounds that they manage. So it's a bit of a mix. Just recently, also just started getting into some oil and gas industry applications as well. Locating large diameter pipes under the surface and being able to represent those and recording informations on maintenance and trenching and so on. So yeah, it's quite a wide variety of different applications.
Absolutely. Very useful technology. Very exciting to see. Can't wait till I can get my hands on something like that myself and play with it. We've got a question from the attendees. Great presentation, Michael. What skills do you look for in employees who will be using this technology?
The employees that use the technology. In many ways, actually, you don't need so much of the map interpretation skills. That was one of the big drivers for us developing this particular technology. As I'd worked for a long period of time in GIS environments, either on software development for some of the GIS vendors, or delivering systems to customers, so doing the database design and implementations and configurations, customization. And it had always been on workstations and in the office. And I realized about 2010-11 that the big deal was that wasn't getting out to the field. And so people were still walking around with bits of paper or PDFs, just the standard dial before you dig type approach we still see today. Unfortunately, the workforce we now have that are digging the holes and doing the directional drilling and so on are not the experienced engineers that we used to have many years ago. 30, 40 years ago, when you had a job with the power company or the telco, you had a job for life and you worked through that organization. You became intimately knowledgeable about how it was connected, how it was structured, how deep it would be, where it was likely to be found, just by looking around and getting familiar with the types of lids or surface features you can see. Those skills have been lost because now all that digging and directional drilling is all done by subcontractors of subcontractors. And the guys out in the field are often, right at the bottom end of the food chain and are often poorly paid, poorly skilled. And many of them cannot read that 20, 30 sets of PDFs that they might get describe what's under there in some area. And it's a good trick. I mean, we've been, you and I have been working in this industry for many years, and so we're probably pretty good at map interpretation, But you get a young guy out in the field who's just recently come to your country, his natural language isn't English necessarily, he hasn't been trained and all this stuff, and ask him where he's standing on that piece of paper that he's looking at, he can't tell you. He can't tell you even often, which direction that pipe or cable is oriented, let alone actually exactly where he's standing. So this de-skills that, takes away that map interpretation, that mental model jump we have to make, which we do naturally now because we've been doing it for 40 years or whatever, but which if you're new to the industry, you have to learn and takes a long time. Whereas the augmented reality approach really means it's much more natural. You can actually, because the device knows where you're standing and knows where you're looking, then in actual fact, all that interpretation is taken away. And now you actually just see where these things are. So it's sort of de-skilled it to some extent.
Do you have full-time 3D modelers setting up the subsurface AR views?
No. That's all 100% fully automated. So when we connect to any GIS server via the internet, then there's a configuration stage where we basically just set up some rules about how to display the stuff that's in some table somewhere. So when we ask the GIS database for some data, it might be coming from a table called W1, which might represent a water pipe. And so we set up a style rule that says, instead of just displaying it on a map as a green or blue line, that we're going to display it as a cylinder, and it's going to have a dimension or cross section that's going to be controlled by some attribute, maybe diam or diameter or whatever it happens to be called. And that if it's 2D, then it'll be put down a default depth. If there's an attribute that actually defines its nominal depth, then we'll use that to put it in its depth. If it's 2 to 3D, then we can display it at its appropriate 3D position. If it's 2.5D or sort of relative, maybe 3D, but relative to the surface. So data you might be getting from a wand or a directional drilling machine, which records depth rather than absolute elevation, then we can project it at the appropriate depth. Yeah, no, there's no 3D modeling required for any of that. It's all fully automated, generates a 3D model on the fly. We do use 3D modelers to generate us nice models of transmission towers or specific types of manholes. But actually now we start getting supplied those quite a lot from the manufacturers, actually. So manufacturers can supply 3D models of some of their assets.
Okay, well, that concludes this presentation. Michael, thank you so much for presenting AugView and your technology. It's been a real pleasure having you with us at SumSF 2022.
Fantastic. Thank you for the opportunity.